Hello viewers, welcome to Obukaniswa's tutorials. I'm Sir Amos and I'll be taking you through solutions to first order ordinary differential equations of the separable form. So, dear viewer, by the end of today's lesson, you should be able to find a solution to a given ordinary differential equations of the separable form. That is, you should be able to find the general and the particular solution to a given ordinary differential equation of the first order. Now, what we need to know in this lesson is to know that y prime is equal to dy dx. That is, if y is a function of x, but if y depends on t, then y prime will be equal to dy dt. You should know this. All right. Now, what are separable equations? When we say a particular first order ordinary differential equation is separable, what does it mean? If it is separable to the layman or to the man on the street, it means that the equation, the variable in the equation can be separated. That is, the x variables and the y variables, or the dependent and the independent variables, can be separated to both sides of the equal sign. Now, a differential equation that is separable is of the form. A separable equation is of the form g of y prime to be equal to what? F of x. So that means that we have the y variables at this side and the x variables at the other side. We have separated them. But as I stated initially, let's not forget that the y prime is equal to dy dx because the function depends on x. If the function had depended on t, then we would have had dy dt to be for the y prime. So changing the y prime, we have g of y dy dx to be equal to f of x. That is for the y prime. So now we can multiply both sides by the LCM, which is dx. So multiplying both sides, we have g of y dy to be equal to f of x dx. So looking at this one can see that we have been able to separate the variables. We have the y variables at the left hand side and the x variables at the right hand side of the equal sign. So at this point, we have been able to separate the variables. So to solve this equation, or to solve these types of equation, after we have separated the variables, then we take the integral of both sides. That is, we integrate this side with respect to y and integrate this side with respect to x. So this is basically how we solve separable forms of what? Equations. So now let's take some few examples and then we see how we can apply these concepts in solving separable equations. We have found the solutions to solve xy prime to be equal to 2y. So this is an ordinary differential equation of the first order given to us, and we have been asked to solve this equation. And now it is an initial value problem which says that at y of 0 will be equal to 3. At y of 0 should be equal to 3. Now let's look at how to solve this equation. To solve this separable equation, what we do is we first separate the variables. That is, we keep the x variables at one side and the y variables at the other side of the equal sign. So that is to say that if we have x y prime to be equal to 2y, then we can change the y prime into dy dx. So that will give us x dy dx. And then we are going to have to be equal to 2y. So multiplying both sides by the dx, we are going to have x dy to be equal to 2y dx. Now, when you study this particular equation, you would notice that we have the x variables combined with y here, and we have the y variable combined with x here. That is not too good for us. So we need to still what? Separate the variables. So that means we have to send the y to this side, and then we send the x to this side. How do we do that? We can do that by dividing. So when we divide here by x, the x will cancel from here and come here. And when we do same for the y will cancel from here and then come to here. So by dividing, we are going to obtain 1 over y dy to be equal to 2 over x dx. So moving forward, we have seen that we have been able to separate the variables to both sides of the equal sign. So the next step is to take the integral. We integrate both sides with respect to. So we integrate this side with respect to y and integrate this side with respect to x. So moving forward, that will give us, this side is going to be the integral of 1 over y. So we have integral of 1 over y dy to be equal to, now this 2 is a constant, so we can factorize it out, bring it back to the back of the integral sign. So that will give us 2 integral of 1 over x dx. So moving forward, we are going to have integral of ln y, that will give us integral of 1 over y, that will give us ln y, to be equal to 2 times the integral of 1 over x, and that will give us ln x, then plus the constant of integration, c. Observe that this is an indefinite integral. So because it is an indefinite integral, we need to introduce the constant of integration, which is c. You can also use your own variable or constant. So now, from here, we want to make y the subject. So we have a law in logarithm. By the definition of logarithms, we know that if I have log a base b to be equal to c, that is here, log y base e to be equal to this, and that is the c. Then a, which is the y here, will be equal to what? B raised to the power c. The definition of logarithm says that logarithm of a number to the base of another number is the power to which the base must be raised to produce the number. So the base must be raised to the number to produce a. So in that same sense, we are going to have y standing in for the a to be equal to the base, which is e. The base of a natural logarithm is e. The base, which is e, to raise to the c here, which is the whole of this one. So that will be to raise to what? But before here, we can still rewrite this one as ln y to be equal to ln x squared plus c. That is from here. That is, we learned that if we have log a raised to the power n, we can write this as n log a. So following that, this particular n can be brought behind, and in that case, if the n is behind, it can also be brought to be a power. So following that, this particular 2 has been brought as a power to make it ln x squared. And now applying the definition of logarithms, we are going to have y to be equal to what? E raised to the power ln x squared plus c. And now by applying multiplication or the laws of indices, we are going to have what? Y to be equal to what? E raised to the power ln x squared times e raised to the power c. That is, when we are multiplying with the same what? Base, we add. So if we have the same base raising to a power, two things adding, then we can bring it to the reverse by multiplying with the same base. So we have y to be equal to e raised to the power ln x squared will give us x squared, then times e raised to the power c. Now, supposing that e raised to the power c is equal to a constant known as c, because e raised to the power a constant is a constant, so we can represent that constant by what? C. So therefore, we have y to be equal to x squared, then c. So this becomes the general solution to the differential equation given. This is the general solution, but what we have been given here is that we have been given restrictions. That is y of 0 to be equal to 3. So we need to put in these values to obtain the value of c here. And that will give us the particular solution. So we say that at y of 0 to be equal to 3, okay, y of 1 to be equal to 3, at y of 1 to be equal to 3, then we have x to be equal to 1 and y to be equal to what? 3. So putting it into the general solution, we are going to have 3 to be equal to what? C1 squared. And we are going to have 3 to be equal to c. So the value of what? C is 3. So we put c as 3 back into the general solution. And then finally, hence, we are going to have y to be equal to 3x squared to be the what? The particular solution to the ODE given to us. So this is how ordinary differential equations of the separable forms are what? Solved. Okay, so we want to take another example by following the same procedure so that we can gain or obtain mastery over it. Okay, so the example 2 says that find the solution to this particular ODE, that is ex squared y prime equal to what? Xy prime. Okay, no, this one is equal to xy. All right, so I think this one wasn't a prime, it is column. So this one says that we should solve this particular solution at the initial values y of 0 equal to 1. So now the first thing we do is to find out whether it is a separable equation or not. That is by attempting to separate the variables. So let's see whether we can separate the x variables at one side and the y variables at the other side. So rewriting the equation, we have e raised to the power x squared y prime to be equal to xy. So changing the y prime into dy dx, we are going to have e raised to the power x squared dy dx to be equal to xy. And so we can multiply both sides by the dx. So we have e raised to the power x squared dy to be equal to xy dx. So we have seen that we have the x and x and there's y there. So the y is at a wrong place. We have dy and we have e raised to the power x squared. So we have to what? Bring the y to this side and bring the e raised to the power x squared to the other side. So we do that by dividing both sides by y and by dividing both sides by e raised to the power x squared. So when we do that, we are going to obtain y over y. We'll obtain y over y, then dy to be equal to x over e raised to the power x squared, then dx. Now this one can be rewritten as 1 over y dy to be equal to x e raised to the power negative x squared. So we can bring it to the top and the power changes, then dx. So we have successfully separated the variables. So the next thing we do is to integrate or to take the integral of both sides. So integrating both sides, we integrate this one with respect to y, and then we integrate this one with respect to x. Now, the integral of 1 over y is going to give us ln y to be equal to the integral of x e raised to the power negative x squared, then dx. So, at this point, we have seen that we have a function x multiplying another function e raised to the power x negative x squared. So, how do we integrate this? We have to integrate this by using integration by substitution. So we take only this portion and integrate it using substitution. Then we fix it back into the equation. So taking only that one, we have the integral of x e raised to the power negative x squared. So we suppose that, so for the integral of x e raised to the power negative x squared dx, we say that let u to be equal to negative x squared. So that is by substitution. So that when we differentiate it, that is du dx, we are going to get negative 2x, differentiating this. So from here, we make the x the subject. So making the x the subject from here, we are going to obtain dx to be equal to what? Negative du over 2x. And therefore, substituting it back into the equation, we are going to have what? The integral of x e raised to the power negative x squared dx to be equal to, we have the integral of x e raised to the power negative x squared is u. And then we have the x to be equal to what? Negative du over 2x. So that will be times negative du over 2x. Now, this x can cancel this x. So in that case, we are going to have the integral of negative 1 over 2 e raised to the power u, then du. So this can be rewritten as negative 1 over 2 outside the integral sign, e raised to the power u, then du. So we integrate this one with respect to u. So integrating e raised to the power u will give us the same thing. So we have half of e raised to the power u plus the constant of integration c. But u was equal to negative x squared. So substituting u as negative x squared, we are going to have what? Negative 1 over 2 e raised to the power negative x squared plus the constant of integration c. So we have the integral for this side to be equal to this. So we substitute it back into the equation. So putting it back into the equation, we are going to have ln y. We are going to have ln y to be equal to what? Negative 1 over 2 e raised to the power negative x squared, then plus what? C. Then plus c. Okay, so we have this to now be the general solution because we do not know the value for c for now. Now we put in the initial values. So the initial values were saying that is we have y of 0 to be equal to 1. So that means that at this point, x is 0 and y is 1. So we substitute them into the general equation, and that is going to give us ln y, which is now 1, ln 1 to be equal to negative 1 over 2 e raised to the power 0 squared. So that will give us 0 plus c. Ln 1, as we know, will give us 0. So we have 0 to be equal to negative 1 over 2 because e raised to the power 0 is 1. Then plus c. So therefore, c will be equal to 1 over 2. C will be equal to half. So now that we know c as what? Half, we can put c back into the general solution that is here, and then we obtain the particular solution. So we conclude that therefore ln y, which is equal to negative 1 over 2 e raised to the power negative x squared plus half, or which is plus what? C. And the c is half plus half is the general solution or the particular solution. Now from here you can equally use the other approach. That is by saying that from laws of logarithms, or by the definition of logarithms, you can write it in terms of y, where we say that y is equal to the base, which is e raised to the power this. Is still the same thing. So that will give us the solution. Or we can also state the solution in terms of plane y. So therefore, this becomes the particular solution. Is the particular solution to the ODE of the separable form. So this is all about solving differential equations of separable forms. So in our next lesson, we are going to look at how to solve the non-separable equations of the first order. So please kindly watch the video, like the video, share the video, and then subscribe to my channel. Thank you very much for your time.